All right. So last lecture we have finished introducing the MapReduce, Spark, those data parallel data processing frameworks, right? And this lecture is intended to give you a detail about how to actually implement a MapReduce program on Hadoop. Okay, and you can see we actually have a lab to show how to operate on such a framework and talk about some detail about some advanced programming skills on Hadoop. However, I used to spend a couple of hours to go through those things, but as I mentioned today, nowadays we don't really use Hadoop that much because, for example, we said that you already can find some Python interface or a connector on top of Hadoop. So all you need is to write a regular Python code instead of actual Hadoop program. And also, people probably use Spark more often than Hadoop. So basically, there are a lot more convenient way to do programming on Hadoop nowadays. You can go through other framework or other library. You don't really need to necessary to write the actual Java code for Hadoop. So I decide to kind of just give you a very brief introduction or go through the content of this lecture. And so you just need to aware of those things. Okay. And I believe in practice, you will able to still be able to use Hadoop through other tools or other interface, as I mentioned. So this lecture become just a kind of a reference for you. If you actually if you are interested in knowing more about the detail of Hadoop, or you really want to do the Hadoop coding on yourself, then you can follow the content from this slides to do some self-learning and self-practicing. Okay, all right. So I will not go through this kind of word by word or slice by slice. Okay, we just quickly went through the content and to let you know what we have in this slice. Okay, right. So first of all, as we mentioned, right, do is an implementation, and today I forgot to update this. Right, we are already at in year 2022, almost 23. So there are some new version, but still we are at 3 point something version. Okay, and as I mentioned, the biggest difference is the jump from 1 point something to version 2, because we only have young after the 2.0 version. So 2.0 is a very important milestone, and the 3, of course, is just getting more powerful, but probably just more features. Okay, and as I said, actually the language for Hadoop is Java. It is implemented in Java. So the content we have, the programming, um, uh, the programming example we have in this slides is also based on Java. But as I said, now you have other language interface as well, like Python, okay, or you could use Hive or Pig we mentioned, right? So you can use SQL or some data flow language to generate the code running on Hadoop as well. So you don't necessarily to write the Java code for Hadoop anymore. Okay, so that's why I decided to kind of skip over this part of the lecture, and you only need to know the basic concept or get the feeling about what's beneath those tools, right? when you want to use Hadoop. So the second thing is Hadoop is a cluster, right? Just like the MPI cluster you have for our class to run the payroll program. So when you install Hadoop, you basically install it on a cluster, right? So that's why you have workers to explore the data parallelism on those workers to accelerate your computation, right? To perform distributed computing. And the head node is a scheduler, right? So if you want to run a Hadoop job, actually you also need to submit your job to the scheduler, to the head node of Hadoop cluster. And the scheduler will schedule the job and the tasks and running on those workers. Okay, so very similar to all the cluster computing systems. Okay, and here you can see, this is the Hadoop package, right? So if you want to really do the Hadoop programming in Java, then you just have to include all those packages in order to write the MapReduce code. Okay, and you can see, of course, there are some older version package and newer version. So you have to be careful which version of package you are using, because they look very similar, but sometimes they are not compatible. Okay, so those are just some tedious issue you might encounter when you actually do the coding. And don't forget, it's an open source project, so it's always changing, right? It's always some feature or API that is they are deprecated, so you are not supposed to use them anymore, or the result is not guaranteed. So those always the problem you have when using those open source solution, and that is why we mentioned for industry. Usually they still rely on some third-party company to provide those service and maintain the system for them. Okay. Okay. And then how you write a map reduce code on Hadoop. You will see that basically, first of all, it's a Java program, right? And we all know Java is a OO language. So what happened is when we write the map reduce code on Hadoop, we try to inherit and re-implement some of the interface provided by the Hadoop framework. So that's what happened. So basically, you can those are the class that you can try to re-implement it, right, under the given interface. Okay, and the mapper and the reducer, right, are the interface that you need to implement if you want to have your own map function and reduce function. But besides that, actually you can override many other functions and interfaces in the Hadoop framework. So that's why you can kind of customize the computation a bit more, right? In order to realize or implement some of the algorithms more efficiently. Okay. For example, the partitioner will decide how you would like to partition the key, into those groups when you do the grouping. And we will see a few more. Okay, and the record reader and record writers are you can override those functions to define what is a record from your file. Okay, so you control how you do the input and output, how you interact with the Hadoop file system or other file systems. Okay, all right. So that's why it's actually not that easy to write a Hadoop. Conceptually, it's easy. You just need to write the map function and reduce function. But in practice, you will find it's very complicated because most of the time you don't see the whole program. You only try to inherit and override some of the function. So you still need to know what happens, right, for the rest of the framework without looking at the code. So that's why it's sometimes hard to understand or to debug the code because you only write part of the code and the problem may not happen from your code. It's maybe because of how your code interact with other components from the framework. That's why it becomes so so complicated. Okay. All right. So I will not go through it in very detail, but the slides will introduce you those basic class that probably will need to re-implement it, or you need to code the method from those class in order to, for example, create your job, submit your job, and even control the job. So you could even delete, or change the scheduling priority of your job. It's all through this job class. Okay. And you can see to submit a job, you can let the job run concurrently to your control program, or you can use a make them run sequentially. Means you will wait until the job finish before you can submit another job. Okay, so it's basically a blocking or non-blocking way to submit the job to the Hadoop framework, okay, or the Hadoop cluster. Okay. So if you are interested in that, you could check out those API, and you can see if you run it concurrently, that means your main program can still call those API to interact with the running job on this Hadoop cluster. Okay. All right, and this is the code, the actual code that you will write in order to submit a job with a blocking submission or a non-blocking submission. Okay, and you can see because this is Java, right? So you have to write those basically write them in this main function, and of course you will compile it right into a binary code called the word count, right? Okay, and as I mentioned, the way to write the MapReduce code on Hadoop is to inherit and re-implement those class methods. Okay, so whenever you overwrite, you need to use those method to configure the setting so that your binary code will link right or to code the function you implemented or the class you re-implemented. Okay, so that means if you write your own map function, then you will have to define your own mapper object, and you have to use this set mapper class to that the Java compiler knows that this method, this interface will be implemented by your code, right? So it all depends on what are the interface you re-implemented, and if you do that, you have to use this to change the behavior of MapReduce program. Okay, and so as I said, the reason it's actually complicated to write a MapReduce program, a Hadoop program, is because you have to know the whole workflow without looking at the code, because you won't see those code. Those code are not supposed to be changed or modified by you. Those are the code that already exist and implemented in Hadoop framework. Okay, but you have to know that, as we said before, the map phase, reduce phase, the behavior, in order to know what happened if you redefine the method for partition, for map, etc. So this is the end-to-end, step-by-step workflow in Hadoop. So you can see the split function is the one that generates the records from your input file. And the map function is what we said, how you convert a record to the intermediate key value pair. And the partition function is the one that decide how to partition those keys to your reducer, right? So usually it's a hash, right? Hash by the number of reducer. So you want to evenly distribute those keys to the reducers. But sometimes you can, for example, you can force the word star with A must be processed by reducer 1, then you can write this partition function to force that decision. Okay, and one of the reasons you want to re-implement partition is because the data distribution of the key, right? Load balancing, again, is important in parallel computing. So the reason we use hashing by default is because we expect the data will be evenly distributed across reducers. But it may not be the case if your data distribution is non-uniform, right? Some of the characters just have more terms or words. So the distribution will become non-uniform and you have unbalanced load on the reducers. So so there are research work that, or probably there are some, maybe even implementation has been done to decide the partition based on the data distribution. So you will consider the distribution to ensure the load is always balanced across reducer. Okay, and combiner. Okay, combiner basically is the same as the reduce function, the functionality, right? That means you try to reduce, merge the result of a key, right? For example, we see two dogs here. So we can merge them, combine them into just one key value pair, just like what we expected to do on the reducer. But why we need to do it on the mapper side? Because remember, usually the performance bottleneck from MapReduce framework is when they try to transfer the intermediate key value pairs from the mapper task to the reducer task, because it's a remote network data transfer. So if we could combine the result locally at each mapper, then we can reduce the amount of data transfer, right, to the reducer side. So it can speed up our computation and reduce network consumption. Okay, so combiner is actually optimization in the MapReduce framework. Okay, okay. Uh, but there are some limitation we will mention. It's not the combiner is still different from the reducer because for the reducer, it is similar to the mapper. We can reduce and generate any output key value pair, even with different data type from the input records, right? We have all the flexibility. But for the combiner, it is only an optimizer. So he's not supposed to change the behavior of the computation. So his input and output must be the same data type. Okay, and also this optimization is not controlled by the programmer. It is controlled by the framework. So that means even thought you define or implement this combiner, whether the combine function will be applied in this computation is decided by the framework, not by the programmer. So it may or may not be applied on your computation. It all depends on the framework. Usually, if the size of the intermediate key value pairs is small, then the framework will not apply combine function because he think the size is small enough, so he will not apply it. But if he find the data size is large, then he may apply combiner and try to reduce the size. But this decision is completely made by the framework, not by the programmer. So you cannot assume the combine function is code in your computation. It's not guaranteed. So it's an optional. So this is why we indicate it's an optional function over here, and it's not controlled by the programmer. So this behavior, in this case, you can see because we simply merge the result together, right? So whether we apply this combine function or not doesn't affect the end result, right? You can see the word count will still be correct. It doesn't affect the results. So that means this combiner is, it's okay to apply this combiner. On the other hand, if you try to write something that if you apply and without no, with or without applying the function will change the result, then that means it's not appropriate combiner because you will not be able to control the result. Okay. All right. So there are some limitations for a combiner. So it's similar to reducer, but still it has more restriction. Okay. All right. And after the combine phase, then we will, as we said, the data will transfer to the reducer side. Okay. And this is the steps for a reducer. Okay. So first of all, you can see he will try to merge, will do the merge sort because he need to merge the right intermediate key value pair to each reducer. Depends on the partition function, right? And when he merge, he will also try to sort the merge result by their key. So that's why you can see we always will try to process bear, right, before cat, then before dog. So there's an order for those keys when they fit into the reduce function. And that's controlled by the merge sort. And the merge sort has a sort comparator function you can modify. So you can either sort the result in an increasing order or decreasing order. Okay, so it's could be modified by the programmer. Okay, and then it's the grouping. Okay, so the grouping by default, of course, that means if the key looks exactly the same, then the values will be merged and grouped together. But it's actually controlled by the grouping comparator function. So you could also override this comparator function to try to do the grouping in a different way. For example, if you still remember, we mentioned a secondary key strategy when we try to implement the secondary sort solution. So that means we only try to compare the key with the probably the first part or part of the key value. So how could you do that? You could do that by override the grouping comparator. So you only compare the first part of the key, not the whole key. Okay, so um, because of you can override this function, so that's why you could implement the secondary sort solution we mentioned in the uh, uh, previous lecture. And we will also see that example again at the end of this lecture. Okay. And finally, only after you do the grouping, then we will call the reduce function to reduce the result for each grouping key, right? Same as we mentioned before for the behavior of a reduce function. Okay, and finally, the writer has an output format you can choose or you can re-implement it to decide how the final key value pairs are written to a file. Okay, for example, whether you want to have a line break after each key, right? It's all controlled by the output format. Okay. All right, so you can see, in fact, on MapReduce, you not only can write the map function and the reduce function, you can also override those functions to change the behavior of the workflow. And sometimes you can use those changes to make your computation more efficiently, right? For example, like the combiner, you can reduce the amount of data transfer, right? Or you can use the sorting, merge sort, so you can sort the data in a different way, the way that you actually need it. Okay, so that's why most of the problem actually is not just return the map function, reduce function, and therefore the implementation could be much more complicated than we talk about in the last lecture when we only talk about the concept of map reduce programming model. Okay. I will not go through this in detail, but you can see every function we mentioned. Okay, this is how you would like to, how you can set the class to the one you re-implemented, and this is the process of the workflow we show in the previous slides. Okay, so you have to know the flow first. and then decide the programming logic, and then finally find the API to implement your thoughts. Okay. So you can see this slide is pretty detailed because it's supposed to let you be able to actually write the MapReduce code. But we'll just quickly go through as a reference for you. So you can see like the input and output format, there are some pre-implemented solution for you. So sometimes you just need to set the class to different one. So you can choose which behavior is the one you want, right? For like input, they have two options. One is to treat the position as the key. The other is to treat. You can decide how to know which is the separator in the line, and the separator, the content before the separator will be treated as the key, and the content after the separator will be treated as value. So that's another way to interpret the key value from a single line, right? So you can choose those different class to have different behavior. Okay, and I'll put just one. Probably there are more, but usually those three, those are the class we needed. They are usually quite enough for most of the use case. Okay, and the key value pair, right? It's just a data struct, so you have to decide what's the actually data type for a key and value, right? So you will see that in MapReduce, in Hadoop, they already define and implement those data type class for you. It's not a primitive type. It's a data is an object, because each of those data object contain many methods. For example, some of them have their compare function inside. So that's why Hadoop can know how to do the comparison on those data. And so, for example, the key object will also extend the interface of a writable comparable object or class. So that's why you have to define and implement the compare function from this data type. Okay, so it's not like you can use any data type as the for the key. Okay, you have to use a class that's extended from the or implemented from the writable comparable class interface. Okay. All right. So this is the complete code actually for word count we talked about before. So you can see there are so many lines of code just to set up the environment, right? To do the right configuration, to make the Java compiler link to the right code. So you can see this not very straightforward at all, right? So that's why people now try to prevent write the code like this directly. Okay, just like we don't want to write assembly code now, right? But we still need to know the concept and know how they will be, what kind of code will be generated, right? Etc. Okay, we still need those concepts. We just don't write the code in such lower level. Okay, all right. And the mapper, we can just quickly look at the code. So this is what we mean. If you want to override the map function, you have to first define your mapper class, which will extend the mapper interface, right? And you will re-implement, for example, just the map function. So that's why your mapper can do a different way of mapping. Okay? And the way to emit the key value pair is through this context. Okay, so you can see through this context, we can call the context write, which will generate or emit the key value pair from this input key value pair. Okay, so this two argument is the input, right? So this shows that a map function will only handle one key value pair record at the time. But you can have a for loop or while loop here to generate multiple intermediate key value pair records, right? Or generate nothing. So that's why it's it's one to many mapping. And the data type can be changed. In this case, word one, right? They are text and int writable. Okay, so you can emit any a record with any data type for your key and value. So you can transfer the data type as well from the map function. Okay, uh, but because we all know Java is a strong typing language, right? So this is another tedious things you have to pay attention to. So it depends on what the data type is, you have to set the data type in your main function. And if anything that's unmatched, you will see the error from your node when you do the compilation. So you will encounter some compile error. Um, so again, you can see this type information is scattered around your code. So that's another reason people don't like to write the Java code. There are so many things you have to take care, right, in order to make sure it's correct. Okay, so the typing is one of the problem you have to pay attention to. Okay. All right, but overall, I believe you can, as long as you know Java, I think you do know, right, what this function is doing, and this is just how you will need to write the code in for on top of Hadoop. Okay, and reducer is similar, so the only difference is the value part is a list of values, right? So you can see the code pretty much the same, except that the values is a type of iterator. Okay, everything else is the same, like the map function. Okay? Right, and then we mentioned you could not control the number of mapper of a map reduced job because it's depending on the input split. Depends on how many data will be, how many partition will be generated from your input file. And one partition will assign to one mapper. So it's actually controlled by your input split function. It's not a configuration that you can just set the number arbitrary. Okay. On the other hand, the reducer could be set arbitrary through this method. And in general, this value should be between 1 and 2 to the number of reduced slots. Usually, the reduced slots equal to the number of core you would like to allow to run the map to run the reducer tasks. Okay, so why is it between 1 and 2? Because if you're less than 1, of course, means you lost the efficiency, right? You have more slots than your task. But why it could be more than 1? Okay, the reason is sometimes those reducer are executed independently, right? So they are not guaranteed to all run it at once. Sometimes you will run it in several waves. So if you have two, then you can run them in two waves, then you can overlap some of the time between the reducers to make sure your resource or CPU utilization can be even higher. But the ratio shouldn't be too high, right? If it's too high, that means you have way more computing tasks than the resources you have. Then you will not have any benefit because your resource already fully utilized. So there's no point to generate more tasks, right? So that's why, as a principle, it's actually a magic number. It's a magic number falls between 1 and 2 based on some experiments. Okay. All right. So that is the basic for Hadoop programming. Okay. Uh, so I have a lab here, and supposedly this lab is running on cloud using AWS. And since AWS cloud is free now you have free trial. Nowadays, you can easily find that. If you are interested in that, you can try to launch a Hadoop cluster on cloud by yourself, and then you can just run the code we provided from the slides, or you can find it from the internet easily, and you can try to run those code. Okay. And the Hadoop cluster on AWS is called the EMR. Okay, so it's really easy to launch this EMR if you look at the documentation. Okay, you just need to click how many nodes you want, what's the version of Hadoop cluster you want to install, and then the cloud will prepare everything for you. And then you just need to log into the head node and start using it. Okay. And of course, we said Hadoop is not just MapReduce, also include the Hadoop file system. So here is the command, right, from HDFS. It's similar to file system, but it's through a customized file system API, not the Linux API, not the proxy interface API. So you have to issue those commands to do the copy, etc. Okay, to interact with the distributed file system. So just remember, this distributed file system is different from your local file system. So wherever you put the file to the distributed file system, you may not see it on your local file system. There are two separate file systems. Although they may both store data on every compute node, but still you have to use different interface to interact with different file system in order to access the file in those file systems. Okay. So we have the step-by-step command, so you can just imagine to see what's the process for us to run a MapReduce program. And as you can see, usually we have to first put our file to the distributed file system, HDFS, before we start running our code, right? This is just some of the result from those commands. And supposedly this is what happened if you put the file on the Hadoop file system. Okay. And this is how you compile the MapReduce program, the Java code we mentioned, and then we have to target, and then we submit it. Right, this is actually a submission. When we say run, this is submit this job file to the Hadoop hand node. So the cluster scheduler will create those tests and start running the program. And you can see the input and output file location actually pointed to the Hadoop file system. It's not a file path for the local file system. Okay. So that the mapper and reducer can read and write the file on their local machine. Okay. All right. So this is the snapshot of what if everything went right. Then this is the result you will see. Show successfully and show the progress of your mapper and reducing phases. Okay. And it provides many statistic counter for you to monitor or diagnose your jobs. Okay. And this just a command to pull the result from the file system from the distributed file system to the local file system before we can show the result on our screen, right? All right, and we said no. Hadoop is an ecosystem, so usually you will also install many other monitoring tool or administration tool, and specifically on the on AWS, it provide all those things already. Right, it's very convenient. So you can use those URL to access other services which provide the status and monitoring your Hadoop cluster. Okay, so basically you can trace the job, you can look at the Hadoop file system and check out the logs generated from your job, etc. Okay, so all those tools actually are developed in an independent project, but when we install a Hadoop cluster, we usually also install all those supporting tools so we can easily manage and monitor and debugging our MapReduce code. Okay, so here are some of the snapshots. You can see how we could use those service, especially the web portal, to interact with the file system or the job, right? This is like the job queue, right? So you can see what the jobs are submitted and their status and their owner, etc. So basically very similar to the cluster we built for running MPI jobs, right? Here is a cluster that built to run the MapReduce job through the Hadoop platform. Okay, and the history server store all the logs. So this is very useful. So you can diagnosis, what happened from each task, right? How many bytes he write, what's the status of the task, etc. So those are important information if you encounter some performance issues or errors. Okay. All right, and we also showed how you could interact with Hadoop through Hive, and it's very very easy. So again, on AWS, you can simply click. You want to install Hadoop and Hive, HBase. There are many other software. You can just click it, enable them, and the cloud service will install all of them on your cluster, and you can just directly use the software. Okay? And for Hive, we said it's a SQL-like language. So you can see those are the Hive query compared into the MySQL query. Very, very similar. Okay. So supposedly it's very easy to learn. And again, when you interact through Hive, it's very similar to interact with MySQL database, right? But the difference is every Hive query, as we mentioned, is actually transformed to set of a MapReduce job and then running through on a distributed system. So that's completely different from a SQL database, which usually only install on a single node and operate in memory. Okay, so you can see we want the user feels no difference, but the underlying technology is completely different. Okay, so as a user, you might not feel too much of differences, but as an engineer, uh, you have to know the detail. And as we said before, because the execution of a distributed system is very complicated, so if you encounter any performance problem, you need to know those concepts in order to understand how to optimize the performance of your application, like Hive. Okay, so so that's why it is much more difficult. It is actually require quite a bit learning curve to master those big data solutions. It's not easy at all. Even so, the interface, the program, the coding looks similar, but it's actually quite different. Okay, similar to Spark. Um, as a user, again, you don't feel anything. It's just writing a Scala language like this. Okay, but again, what's different is your code is through Spark now can be run across machine, across data centers. So that's why you can handle and solve the big data problem. Okay, but supposedly you only need to know how to write a Scala program. Okay. All right, so we show you a couple of examples how you could write a Scala code for word count or pi estimation. Remember, this is the code for your lab one when you try to learn MPI, right? If you write it in Scala running on Spark, this is the code you need to write. Much simpler, right? But it actually can do exactly the same thing as what you did in lab one when you do the programming using MPI. Okay, but it's supposedly much more convenient for the user, right? Okay, so more example for you to reference. Okay, all right. So that's about the um, how you can actually use um, a tool like Hadoop, Spark, and Hive. Okay, and we have many references for you. So if you someday if you actually need to write a Hive program, Spark program, at least you have the concept and you can reference to those material to learn by yourself. Uh, but from my point of view, the most important thing is the understanding of the fundamental of parallel computation. And hopefully you already mastered that through the through the first half or the uh, through this course. Okay, so supposedly those are just some other tools for you to to utilize your knowledge. Okay, and to implement anything you want to implement. Right. All right, and finally is the advanced programming. This part is to show how you could override other functions in Hadoop, right? Like the combiner, partitioner, etc. Okay, so I will not go through the coding part. If you have time, you can just read them. But basically, all those optimization or all those techniques are quite common if we want to implement some algorithm efficiently on MapReduce. And I will just let you know what's the purpose of each of those technique. Okay, so the first technique is try to customize the data type for your key or value. For example, if you want to define a data struct for your key or value, right? For example, if your data is a three-dimension coordinate, right? You don't want to store it as three independent data. You want to store them in a data struct like this, right? It's not an integer. It's not something has been defined and implemented by Hadoop. And so how could you do that? So you can do that by, you can see, define your own data type like this, okay? And so to be able to read the data directly into memory in this format or in this data struct. So you suppose you can simplify your code, right? And to avoid some of the data serialization or deserialization operations, okay? So anyway, uh, Hadoop actually allowed you to define and implement your own data type for storing key and value. Okay. If you are interested, you can look at those pseudo. It's not pseudocode; it's actual code. Just look at those code to know the steps. Okay, and what you need to do. Okay. All right, and so this is for value and for key. The only difference, you also have to implement this compare to and hash code function, because those are the one that will be used by sorting and partition function in other component. Okay, so you can see this is the complete code for the point 3D data type. And you can see this is a 3D coordinate. So when we do the comparison, here we define it's the distance to the origin. Okay, shorter means the value is smaller. Okay, so that's why we have to calculate some Euclidean distance, etc. Okay, and for hashing, we have to do some serialization, deserialization before we generate the hash value. Okay. All right. That's example. For example, here's an example for the case. Say, if our input is a list of coordinates. If we define this data type, also we write many code to define this new data type, right? But after we do this, we actually don't need to modify the map function and reduce function at all, because you will see the goal is to, for example, sort the data, right? Sort those coordinates by their Euclidean distance. So all we need is to ask the Hadoop function, the Hadoop framework, to read out those value and write out again by a single reducer, because the framework will sort by key. so it will automatically sort the result. And so we don't need to do anything. You can see we don't even have a mapper function or reduce function. We just need to use the default behavior to generate the results. Okay? So you can see this is probably better than you to process the data in the map function and do all those things. Okay, um, so that's why sometimes we want to use different data type. Okay? And combiner and the combiner and the partitioner is easy to understand. As we mentioned, partition is just decide how you would like to distribute the key to the reducers. So by default, this use the hash function, right? You define it by the data type, and of course you can rewrite this easily, right? And so just remember, if you re-implement the partitioner, you set your new class in the map function. Okay, so you can use the function, whatever the function you implemented to do the partitioning. Okay. So one example is, say we we partition the character from A to maybe H to reducer 1, and the rest of them goes to reducer 2. We can do that control by changing this function. Okay. All right, and combiner, as we mentioned, the most important thing is it's an optional step. So you cannot assume it's always apply. You can apply multiple times or even 0 time in the computation. Okay, and there are some limitation. The most important one is the input and output data type cannot be changed because it's an optional step. Okay, and some of the things, if you apply combiner, can generate different result. For example, if you want to compute the median, right, or the average, right? If we use the combiner to do the local average and then use the reducer to do the global average, the result will be different, right? Like if we have 1 through 5, if we do this result will be different from this one. So that means we cannot compute the mean at the combiner. You have to do the mean at the reduced phase. Okay, it cannot be done at the mapper phase because it will change the results. Okay, so you have to be more careful. In short, okay. Finally, is the sort comparator. It decides how you want to do the sorting, and basically you can change the sort comparator function. So for example here, this is the case for a composition key, right? You can see, assuming the key looks like this, right? As a composition of string 1 and 2. And when we do the sorting, if you only want to sort by the first part of the key, we can re-implement the sort comparator as shown here. So you can see we only compare the first part and ignore the second part. So that's why we can just sort it according to the first part of a composition key. Okay, and this is what we need if we want to implement a secondary sort on Hadoop. Okay, and far as the grouping, similarly for grouping, in this case maybe we only want to group by, again, the first part of the key, and we can do that by, again, writing the compare function like showing over here. Right? Similarly, we try to compare. We have to compare. We have two. Basically, we have two key. The compare function will decide, given two key, which one is larger and which one is smaller, right? And the result will be used to determine whether those two, the value of those two keys should be grouping together. Okay, so actually the result only matter whether it's 0 or non-zero. 0 means they will group together. Non-zero, they will not group together. All right, so this can decide whether you want to group together or not. All right, so finally, secondary sort. We already saw this in our, if you remember, when we built the inverted index, we mentioned we want to sort the values according to their document ID, right? And that's a secondary sort problem. And here we can see it again. For example, we have this temperature records. We want to output this result to show what the temperatures has recorded for each month. And we want the recorded value to be sorted according to the temperature. So you can see the result not only sorted by the key, but also sorted by the value. So sorting by value is the problem called the secondary sort. Okay. And so this is a problem that very commonly seen when we try to analyze data, right? Even in our inverted index example, we also require this. Okay. And the solution is what we mentioned, but now I think you know how you could implement it. So on Hadoop, okay. And the solutions that as we mentioned, the first solution is bad. This solution just put everything to the reducer and sort it in the memory of the reducer. So if you have too many records, you will have the OM problem, like we mentioned before. So what we want is use the composition key. We also repeatedly saying this already several times. And the strategy is you can see in this case is basically the strategy is to include the value you want to be sorted to the key, right? So the MapReduce framework will not only sort by key, but also sorted by value, okay? And the complete result is like showing over here. When we read any record, the mapper will convert it to a composition key, right? As shown over here. Not only we have the month and the year, we also have the temperature as a key, as a part of the key. So this is a composition key. Okay. The value is still just the temperature, but we use the mapper to generate the composition key. And because of the behavior defined by MapReduce framework, so we know what happened is when we will have to override the partition, right? We have to override the partition function so that it will only look at the first part of the key to do the partition, so that we can ensure no matter what the temperature is, as long as they are from the same month, they will send it to the same reducer. So therefore, they have a chance to be grouped together as a single key to the reducer, right? So that we can generate this aggregated result. So the default partitioner will hash it, right? Will hash it based on all the value in the key. So that will scatter this result to different reducer, and that will not achieve what we want. So we have to override the partition function to ensure it's only hashed by the first part of the key. Okay. Same thing for grouping function. We only do the grouping according to the first part of the key. So that's why they can collect all the temperature on the same month together for the reduce function. Okay. And remember the framework has a sorting. By default, you will use a merge sort, right? So that's why after we do those grouping, when they send it to the reduce function, you will sort it by the first part of the key first, and then the temperature. And of course, for those records in the same group, the first parts are the same, but the temperature is different. So it was sorted by the temperature, okay, and send it one-to-one to the reducer. And the reducer actually don't need to do any sorting anymore, because the values is already sorted by the framework. So all the reducer needs to do is to output the result, right? take out the information that we don't need to show in the output file. So this is how we can implement the secondary sort efficiently on the Hadoop framework. Okay, and in order to do that, you can see we have to override the partition function, the grouping function, and the sort function. Everything we mentioned before has to be override in order to realize this solution. Okay. All right, so that's it. So we'll just show you the example to let you know why sometimes you cannot just override the map function and reduce function. In order to make it efficiently, in order to make sure the computation is efficient, sometimes you have to explore all those capability and to rewrite those functions to control the behavior and to get your results. Okay. All right. So it's not easy to implement a map function. So a library like for example, we mentioned there's a MLlib, right? Or there are other projects that try to provide machine learning library on top of MapReduce. It's hard because for every machine learning algorithm, you have to figure out what's the best way to implement them on Hadoop. Okay, so there are many papers to discuss and to to show what's the most efficient implementation of a certain algorithm on Hadoop. Okay, and so probably 5-10 years ago, there are many papers working on that problem. Okay. All right, so that's a quick overview of how you can implement Hadoop, right? So we'll take a 10 minutes break. So we will come back at 4:45, and then we will start the final lecture of this course.